also how many possible groups of 2 men could be chosen and how many possible groups of 2 women could be chosen, and that will help us solve the problem. Okay, so 11 choose 2, I'll write it this way, is going to be the number of ways 2 people can be picked from this group of 11, regardless of whether they're men or women. The formula would say that's 11 factorial divided by r is 2 factorial times 11 minus 2 factorial is 9 factorial. Now think about this. 11 factorial is 11 times 10 times 9 times 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1. In other words, it's 11 times 10 times 9 factorial. 2 factorial is 2 times 1. 11 minus 2 is 9. You already have a 9 factorial on the bottom. You can calculate this without a calculator. This is 11 times 10 over 2. 110 over 2 is 55. With 11 people or 11 objects, there are 55 possible groups of 2 objects that could be chosen, in this case 2 people. Okay. How about the number of possible ways of choosing 2 men? There are 5 men. The answer would be 5 choose 2. 5 factorial divided by 2 factorial times 5 minus 2 factorial is 3 factorial. 5 factorial is 5 times 4 times 3 factorial. And that's going to cancel with the 3 factorial on the bottom. So you're left with 20 over 2, which is 10. And then how many groups of 2 women can be chosen? That would be 6 choose 2. 6 factorial divided by 2 factorial times 4 factorial. 6 times 5 times 4 factorial divided by 2 times 1 times 4 factorial. The 4 factorials cancel. You get 30 divided by 2, that's 15. Okay, so this is the number of total possible groups of 2. This is the total number of groups of 2 men. And this is the total number of groups of 2 women. How about the total number of mixed groups? Total number of mixed groups, think about it, would be 55 minus the sum of these two. Total number of mixed groups. You don't have to think about combinations there. Take the total number of groups of 2, these groups of 2, minus the sum of the total number of groups of men and the total number of groups of women. 2 men and 2 women. 55 minus 25, this is 30. Okay, that's the total number of ways that you can have mixed groups of 2 in this problem. Alright, now we're ready to calculate the probability mass function based on this. I'll go back to calling it little p. The little p of 0 is the probability that capital W equals 0. Think about this here. There's 55 total groups of 2 people. Having 0 women means you have 2 men. There's 10 possible groups of 2 men. Assuming this is truly a random choice, this probability would be 10 divided by 55. And that 11 is half divided by 5 would reduce to 2 11ths. Okay, so that's p of 0. P of 1 is the probability that capital W equals 1. Excuse me. That's going to be the total number of mixed groups of 2 divided by the total number of groups of 2. 30 divided by 55. Divide the top and the bottom by 5, and that reduces to 6 11ths. Finally, P of 2 is the probability that capital W equals 2. That's going to be 15 divided by 55. And that reduces to 3 11ths, and you can just glance over these and see very quickly that the sum of those is 11 11ths, which is 1. Okay? This is your probability mass function, and we can now use it to find these expected values, these moments, first moment and second moment. Again, we talked about the first moment in the last video. Expected value W, also denoted by mu. Okay, that's another symbol for the mean or expected value. It's a sum of what? It's a sum of the values of W times the corresponding probabilities. In other words, W can be 0, 1, or 2. I'll use a little w here instead of capital W. Okay, capital letters are reserved for random variables. The corresponding lowercase letters are reserved for their values. Add up the products, little w times P of little w. In other words, this is going to be 0 times P of 0, which will of course be 0 in this problem, because W could be 0, plus 1 times P of 1, plus 2 times P of 2. So that's 0 plus 1 times 6 11ths, plus 2 times 3 11ths, gives you 12 11ths, which is about 1.091, turns out. That's 1.09 actually, with the 0.9 repeating. 12 divided by 11. There you go. Alright, it's not a whole number. You should expect it to be a whole number, pun intended. Okay. Even though it has to be a whole number itself, on average, the mean, the long-term average, if you do simulation, it doesn't have to be a whole number. Okay, that should make intuitive sense. I mean, it runs the most. 0s and 2s not equally likely. Okay, so on average, you're not going to get exactly 1 for an average. You'll get something slightly higher than 1 because the probability of equaling 2 is slightly higher than the probability of equaling 0. What about the second moment? The expected value W squared. The formula for this is the same formula for the expected value W, except replace this W with W squared. Like that. That's a W there. So you get 0 squared times P of 0, plus 1 squared times P of 1, excuse me, plus 2 squared times P of 2. 0 plus 6 11ths, plus 4 times 3 11ths is 12 11ths. The answer is 18 11ths. 18 divided by 11 is 1.63 with the 63 repeating, so about 1.636. Okay. That's on average the value of the number of squared women. Okay. And again, we'll see in future videos, not too far from now, that this is useful for measuring the spread in the distribution of W. Something called the variance is the most basic measure of spread. That's a little hard to interpret. Something easier to interpret is called the standard deviation of the random variable. That's that's a little easier to interpret. I think I'm going to go fit this all on one page here. I'm using my space wisely here. So that's the first and second moments. Before we explain and generalize, I should say that in general, the kth moment of the random variable is the expected value of the random variable to the kth power, for k. It could be 1 or 2 or 3 or 4 or 5, etc. And that would be the sum in this case. W goes from 0 to 2 of w squared, w to the k power times p of w. Are higher moments useful? No, they end up being useful, especially the third and fourth moment. I'm not sure of applications of higher moments past the fourth moment, although we will talk about something called moment generating functions eventually, where all these ideas can come into play. Alright, let's take a breath. Explain and generalize. So what I want to do is I'm going to explain this formula. Oh, I wanted to do one more thing before I do that. I wanted to check these answers in another way. Let's do that here next. P of 0, the probability that W equals 0. That equaling 2 11s could be checked in another way with the general multiplication. Think about it. Okay, you got 11 people, 5 men, 6 women. W equaling 0 means you didn't pick any women, you didn't pick a man. That means you picked a man with the first person chosen, and you picked a man with the second person chosen. 5 men, 6 women. The probability that the first person is chosen to be a man is 5 11s. Then the conditional probability that you choose a man in the second choice, given that you chose a man for the first choice, would be like about 4/10, because there are 4 men left to pick out of 10 people total. This product is 20 out of 110, which is 2 11s. Same answer we got here. Okay, so this can be solved without combinations. You can think about it in a similar way for, say, P of the probability that W equals 2, and then just add these and subtract from 1 to get this one. Okay, I'll leave that to you. What about this formula then? Okay, this is going to get a little theoretical here. The formula for n choose R. Okay, so you want to imagine you have n objects, where n is 1 or 2 or 3 or 4 or 5, etc., positive integer. So there are n objects. The objects in this case of this problem were people. And you choose R objects for R some positive integer smaller than n. Okay? Though it actually could equal n itself. And you wonder, how many ways can this be done? We're choosing the objects, the order that we pick them in, or that we put them in, it doesn't matter. However, that order that we pick or put them in is going to help us derive this formula, thinking about that ordering. The number of ways of doing this is what I'm calling n choose R, NCR. Again, sometimes written like this. Okay, and I want to see y equals this. Okay. To help us again derive the formula, let's imagine thinking about order, like I mentioned just a minute ago. Choose and order as a separate problem. Okay, and the number of ways of doing that is called a permutation. And we'll talk about permutations a lot more in future videos. I guess you could think of this as an introduction to them. How many ways can that be done? These are our objects, by the way. It's based on something else called you might call it the multiplication principle. Yet another concept here. Think of it this way. Pretend there are 11 objects, these 11 people, and you're thinking about choosing 2 of them. There are 11 people that could be chosen for the first choice. But then there are 10 people left to go in the second spot, so to speak, when I'm thinking about actually putting these people in order. 11 times 10, 110 would be the answer for that. What if you were choosing 3 people and putting them in order? You've got 11 for the first choice, 10 for the second, 9 for the third. The product of those, 11 times 10 times 9, would be the number of permutations of 3 objects, 3 people, from a group of 11 in this case. In general, this number of permutations, which you could call NPR for permutations, is n times n minus 1 times n minus 2, just like I was thinking about 11 times 10 times 9, etc. How many of these are there? There's going to be all of them because you're choosing R objects. Look at the pattern here. The first factor is an n minus 0. The second factor is n minus 1. The third factor is n minus 2. The rth factor would be an n minus r minus 1, which is also equal to n minus r plus 1. Okay? So that's one way to think about choosing and ordering R objects. Another way that I can think about it, that kind of comes from over here. I can first choose the entire group all at once instead of one at a time. There are NCR ways of doing that where I'm not saying what this equals yet. And then once I've got those R objects, I can put them in order. Once I've got those R objects, that smaller group, I can put them in order. NCR ways of choosing the entire group. Here I was thinking about ordering them right away. Here I'm not. I'm taking the entire group right away. But once I've got those R objects, how can I order them? How many ways can I put them in order? I've got R choices for the first slot, R minus 1 for the second, R minus 2 for the, etc., down to 3 times 2 times 1. Hey, that's R factorial. You can solve this equation for this. Divide both sides by R factorial. And NCR will be NPR divided by R factorial. That doesn't look the same as this, but they actually are if you think about this expansion of NPR and do a little bit of clever manipulation. To be n times n minus 1 times n minus 2, it's down to n minus r plus 1 divided by r factorial, but hey, I can multiply by 1 in a disguised form, multiply this by n minus r factorial over n minus r factorial. And if I do that, I don't change the value of the expression, and the top becomes, think about it, that becomes n factorial, right? And try with examples, pick n to the 11 and r to the 2, for example, and you'll see that it works. That is n factorial. Just similar to what I was doing up here when I was canceling the 9 factorials, and the 3 factorials, and the 4 factorials. Those are playing the role of kind of what I was doing with the sort of n-canceling in this song here. This simplifies the formula from the top. This is n factorial divided by r factorial times n minus r factorial. Okay. I just barely made it on my paper. Alright, let's go to Mathematica. And first I'll show you some stuff I've already shown you in previous videos, but then I'll show you something new. Well, actually, there is something newer here right away. In Mathematica, at least, binomial is choose combination, okay? Because these things are also called binomial coefficients, that's the reason. So this binomial 6 2 should be 6 choose 2, which we found to be 15, and it is. Now, seeing the 6 factorial divided by the product of 2 factorial and 4 factorial. What I'm doing here is I'm defining the probability mass function in a neutral way. This is my generalization for this problem. I'm using these choosings, the binomials. Again, this is essentially 6 choose 2. In 3 situations where w equals 0, 1, or 2. To equal these things, these are probabilities. Now, what you see in here that's a little weird, besides the just weirdness of all these formulas, is that I'm also allowing the total number of men and total number of women to be something that I can change. Okay, by putting an m here, that's the total number of men, and a w here, a capital W, that's the total number of women. I'm going to allow myself in Mathematica to make changes to those if I want. Okay, so I'll enter this function. We had in the problem itself 5 men and 6 women, so these are going to be the values of the probability of this function: 2 11s, 6 11s, and 3 11s. Here are the values of, well, first of all, the sum of the probability mass function values, which should be 1. The mean of first moment, the second moment, we should get what we got before: 12 11s and 18 11s. We have approximations to those. And we can confirm, we can actually, this is something different here, we can actually compute the first and second moments in general for an arbitrary capital M and capital W, which again represents the total number of men and the total number of women. And get a formula for it. And we're going to formula for the second one. You might want to do an exercise and check if you can get those things. Okay, when for an arbitrary M and an arbitrary W, again, binomial M comma 2, for example, really means M choose 2. This means really M plus W choose 2, which in our problem was 11 choose 2, etc. We should think about why this works. Here's an animation showing the values of the PDF for different capital M and different capital W. Okay, I can change the total number of men and the total number of women, and I get different PMFs. Sorry, it's a PDF, but it's what we call a PMF here. And I get different means for the values of the mean, center of mass. When W is 0, you've got no change. Your probability that W equals 0 is 1. Okay, you got 100% chance if there are no women, you're going to not pick any women pretty quickly too. On the other hand, if W is 10, for example, and M is 0, then you've got a 100% chance of W equaling 2. Okay, so that should make sense as well. One more thing to do, and that's to show you that you can do some simulation. I'm not going to explain this, but just appreciate what I was telling you. I can define in Mathematica a probability distribution using my PMF here for these values of W, 0, 1, and 2, the ones at the end here, because I'm just sort of telling you to step up by 1 each time. And we're actually using something called random variable to do the simulation. This is going to generate data, 10,000 data points, a bunch of 0s, 1s, and 2s. There we are, wow, really quick, a bunch of 0s, 1s, and 2s. These are the data values. Now, they should correspond to the PMF, and for example, the probability that W equals 1 was 6 11ths. The majority of these numbers should be 1s. If you glance over it, it does look like mostly they are 1s. Okay, that's the values of the data here. I can also square those values. Data squared, now I get a bunch of 0s, 1s, and 4s, mostly 1s again, because these are squared values of W, okay, 10,000 of those. And I can calculate the mean of both the values of W data, I'm calling it, and the values of W squared, data squared. And these numbers, 1.1 approximately, and 1.67 approximately, should be close to the true theoretical means that we found earlier. 1.1 or 1.19, yeah, 1.1 if you rounded, and then 1.67 we got down there for our data, and this is 1.64, so very close. By the way, if I run the simulation again by re-entering random variable, I will get different data and different means, whilst these numbers will change now. Yeah, change ever so slightly. Okay, that's the nature of simulation, is you're not going to produce the exact theoretical results, but they confirm that the theoretical results are reasonable. Thanks for watching this long, jam-packed video. Hey everyone, this is a video about my two latest posts at my blog, Infinity is Really Big. The first post that I want to show you, I won't spend a ton of time with. It's about long-term actuarial mathematics, and I want to show it to you because it includes what I'm calling my, well, currently at least my favorite animated graph. It's a really cool graph, and I give you a little bit of an idea of what it's all about. The second post is what I want to spend the most time on for this video. I'm going to go through the second section of my linear algebra book. It's called Visual Linear Algebra Online, and the second section is about vectors and vector algebra. That's what we'll be spending the most time on in this video. I'll be going through that post and helping you understand it. But before we do that, let's look at the first post. This one right here that's titled Linear and Trigonometric Force of Mortality. It's part 1.11 on my series on studying for actuarial exam, LTAM, standing for long-term actuarial mathematics. And again, this graph that you see here, this animated graph, is what I'm calling my favorite animated graph, at least at the moment, until I come across something else that I might like better. I'm going to give you a little bit of an idea of what this is about. I'll click on this post. To fully understand this, you need to understand some probability theory, especially continuous random variables. If you don't know about that, if you don't understand it, just try to get a little glimmer of what this is about. The main thing I want to focus on here is the trigonometric force of mortality. Now, what is a force of mortality? A force of mortality is basically a function that can be low in value or high in value. When it's high in value, it means that a person or an object like an air conditioner, for example, an appliance, has a relatively high chance of failure in the next short period of time, maybe the next day or a week or so. And when the force of mortality is relatively low, the corresponding probability of failure in the next day or a week or so is relatively low. And while trigonometric force of mortality is not useful for human lifetimes, I'm thinking it could be useful for the lifetimes of things like air conditioners and furnaces that are subject to stresses that vary over the course of the year. For example, an air conditioner is going to be more stressed during the summertime than it is during the wintertime. And so it could be sort of like a sinusoidal trigonometric force of mortality might be applicable to such a situation. So if you look at this formula here, this is what I'm talking about with the trigonometric force of mortality. Mu sub t, it's a function of t, is a times cosine of bt plus phi. That's in parentheses of the cosine function, and then a plus c out in front. I'm going to typically actually take phi to be 0 just to keep it simple. There's your typical kind of sinusoidal function whose graph is going to be a wave going up and down. And we can try to find what's called the survival function corresponding to that trigonometric force of mortality. And this is the thing that is my current favorite animated graph. It's a function of t. So you see the horizontal axis is labeled with a t here. That does represent time. You see these three different sliders in this animation, b, c, and x. B represents is related to the rate at which the force of mortality is oscillating. When B is higher, the force of mortality is oscillating faster. When C is related to sort of what's called the midline or average value of the sinusoidal force of mortality. When C is higher, you have a higher overall chance of failure in the coming day or week or so. But the most important thing to me here is x changing. Now, what is x? X represents actually the current age of the, for example, air conditioner. And as x increases, it means the air conditioner or furnace or whatever is getting older. And the cool thing about this graph to me is what happens, especially when x changes, which is going to happen here in just a second. You see the graph sort of combining a horizontal translation to the left with a vertical stretch. And it's kind of just a really mesmerizing graph. When you watch it, especially as x changes, your eyes kind of glaze over and it can kind of lull you to sleep. I think it's a really cool looking thing. I really like watching it as x changes. It's not a periodic graph in t, but it is really a periodic graph in x. As x changes, the graph is repeating itself. As you continue increasing x, go ahead and watch it here again. X is about to change. Starting graph, and now as x changes, you essentially get the same graph over and over again as x changes by a certain amount. I think it would be, in this case, should be b is set to 0.25. That would be 2 pi over 1/4 would be 8 pi perhaps would be the period in x. Can't quite tell that just by looking at that, but that's something that you can check. Okay? So anyway, it's kind of a cool graph. I think it's really cool. Before I look at the linear algebra content, I will say that I've also done some research with a student related to trigonometric force of mortality, and we come up with some pretty amazing formulas. At some point, I might try to share some of these formulas on this blog, but they are pretty complicated. Alright, the rest of the time we want to spend on vectors. Okay, so again, this is section 1.2 of my online textbook, Visual Linear Algebra Online. I'm trying to, again, write about one section per week. That's my goal, over however long it takes, maybe about a year or so. And this is, again, section 1.2. Section 1.1 I posted last week, and I made a video on that you can find on my YouTube channel, Bokini Math. One nice thing about doing books online for you, certainly is that it's free. Another nice thing is that if I make mistakes, you can let me know my mistakes. So please, if you find a mistake, if you think it's a mistake, send me a message. You can subscribe to my blog. You can also send me an email at bokinimath@gmail.com. Let me know if you think if I find a mistake, and I'll take a look at it and fix it if it really is a mistake. Okay, and that can include misspelling and grammar mistakes as well. Alright, so what do we have here? So I'm not going to read this to you. Okay, you can pause the video and read it if you want, or better go to my blog and read it yourself. But let me just, like I did in the last video, just give you a summary of things, emphasizing what is the main important thing to get out of this. So this is again titled Vectors in 2 Dimensions. The first post, section 1.1, was about points and coordinates in 2 dimensions, and especially something called slanted coordinates. I don't really get into slanted coordinates in this section, but I will ultimately come back later in this book, and it is a really important thing. In fact, I said it's one of the most important things to get out of linear algebra. But here we're talking about vectors. What is a vector? A vector can be briefly described as something that has both a magnitude and direction, a size or length and direction, okay, a quantity that has